Okay, everybody, please turn in your quiz from last week. Sometimes I just like to tease you, keep you on your toes. Get your heartbeat going before we slow it down. Ready? Funny story. Tuesday morning, I taught a lab downstairs, and this student just kept kind of like wandering by, and then eventually he came all the way in and said, "Your computer is projecting in our room." And I was like, "What do you mean?" I was in the middle of my pre-lab talk, and he said, "I don't know. Like, we're in anatomy class, but we can see your screen." And I was just taking attendance, but could you imagine if I was grading or reading my emails or something?
Oh my god.
And it's because last class, I didn't want the projector on while I'm writing over it, so I just kept turning it off rather than stopping sharing on my computer. So it like stayed connected overnight all the way until the next morning. And then when I opened my computer again, as soon as the instructor in here turned on the projector, it started presenting.
And there's not like a signal?
It didn't notify me. That little window never popped up. Nothing.
And there's no like a range limitation? Like it was
No, it's connected by the internet.
That's
And the other instructor couldn't like kick me off. All they could do was share present, like co-present. It was weird, but anyways, I learned my lesson. I didn't. I did the same thing last night. And this morning I opened it, and sure enough, I looked and I was like, "Oh, I'm still presenting in the classroom in the library, or in the gym. Great." All right. So we wrapped up section 1 on Monday. Remind me where we left off. What was the last thing we covered before we left? Good. And I wanted to give you some more common examples of bond line structures and condensed structures. And I'm going to ask that you not draw the Lewis dot structures for them because it just takes too long. So some really common bond line and condensed forms. This is a 6-membered ring with alternating double bonds. To be quite honest, it doesn't matter where you put those double bonds. And off of this, I'm going to draw a bromine bonded to one of the carbons. There are 2 ways that we can condense this. We can say C6H5Br. So we just take that 6-membered ring with 5 hydrogens on those carbons and the bromine. And if we wanted to, we actually refer to this 6-membered ring as benzene. It's a phenyl group. And so we can also refer to this as PHBr. That's another way of condensing it, but it utilizes nomenclature, some system of naming that you need to be familiar with. So I want you guys to recognize that. That 6-membered ring with alternating double bonds is a phenyl group, and you could abbreviate it as C6H5. If we had this 4-carbon chain with an OH group attached on one of the ends, the condensed form can be written as CH3, CH2, CH2, CH2OH. Some people will write it as 2 CH2s with parentheses to indicate kind of that repeating CH2 unit before you get to the end. Sarah, can you tell me how many carbons are in that last structure? Where are you counting? Is there one here? There is. So 1, 2, 3, 4. This is an end. or maybe you'd call it a bend. But notice that there's no other atom explicitly stated. It's not a halogen, it's not an oxygen, it's not a nitrogen. There is an atom here at this bend that is bonded to a carbon and double bonded to an oxygen. Do you agree? 5 carbons. Natalie, on this carbon, are there any hydrogens?
Yes.
How many? 2? How many bonds do we explicitly see? 3. 1 single bond, 1 double bond. How many more to fill its octet? Just 1. Good. You guys see how this can be an exercise, right? To learn how to communicate with bond line structure. Okay, so we can abbreviate this as CH3. Again, now I've got actually 3 CH2 groups in a row. And then at the end here, we'll abbreviate as CHO. And it might feel like, why don't we call it COH? Well, when you see OH, you should almost always be thinking about some OH group. There's actually no O bonded to H here. So it's written in a way that helps you think of the C is bonded to H, and also the C is bonded to O. If you take condensed form and you try to work it backwards into a bond line structure, you'd realize that this carbon has to be bonded to one of the, oh, I made a mistake here. Yeah, it should be 3, not 2. Subscript 3, parentheses 3. This carbon must be bonded to one of the CH2 groups in sequence. It must be bonded to the hydrogen. That's only 2 bonds. So that means to the oxygen, it must have 2 bonds as well. Here's some other common bonding patterns. A CO double bond, where the carbon is also bonded to an OH. Here we get CH3, and we write it 2 ways. COOH or CH3 CO2H. And in this way, we do write OH because there is an OH bond. There is an oxygen bonded to hydrogen. This first condensed form might make you think that it's carbon to oxygen to oxygen to hydrogen. But if you started to build out that bond line structure, you would realize that doesn't satisfy all of carbon's bonds. So I'm giving you the heads up now. This condensed form has a CO double bond. These oxygens aren't in sequence. Okay, here's one that I want you guys to try and work backwards on. Can you build the bond line structure? I haven't taught you what those parentheses mean, but it's really just meant to draw your attention to what we're looking at, something that otherwise might trip you up. So give it a shot. Can you draw the bond line for that condensed structure? All right, turn to the people next to you. How far did you get? What tripped you up? What do you know? What do you not know? Okay, what did you find out? How is that C and O connected? What's this? Oh, a carbon to an oxygen to a carbon? No. But that's actually why we put it in parentheses, to draw your attention to it, to make you realize that this O is actually only bonded to one of the carbons. So
it's to break up it and it's to figure out its location.
it's kind of draw your attention to the fact that it's not going to be a sequence. Here's what we do know. There's a CH3 group bonded to a carbon. And then there's a benzene ring that is also bonded to that carbon, which is why we put the oxygen in parentheses so that you don't think this this benzene group is bonded to the oxygen as well. So here's that one carbon, here's the benzene ring that's attached to it. And then that C and its oxygen, they share a double bond. Tricky, right? Now here's what Belen was actually working on or thinking of. Those of you in the organic lab, you've already worked with this chemical. Some of you might have had an allergic reaction to it, actually. Can you draw its bond line structure? Notice, no parentheses. Also think about how many bonds everything has. And not to linger on this too much, but if we had tried to put this oxygen in sequence before, CH3C, that doesn't have any other bonds going to it. There's no H's with it, so it would never be satisfied, right? That's why it had to have the double bond and the two carbon groups. That was a terrible read. Anybody feel brave enough to draw their bond line structure for this compound on the board? Yoon. Good work. Thank you. CH3, CH2, oxygen, CH2, CH3. Great job. All right. Starting to feel a little bit more comfortable with our language, our assumed structures. Great. Okay. We're moving into section 2. Wrapping up our unit 1. And I want to remind you guys about some of the things that we're going to be doing, but I'm almost too nervous to turn on the projector. So remember, the learning objectives sheet is posted at the top of our module. We're going to be looking at partial charge character. That should be a review. And then we're going to be looking at types of acids and bases and their characters. So let's start with partial charges. Who remembers partial charges from their time in general chemistry? Yeah? This is an effect of what, Will?
The uneven attraction of electrons between molecules of different electrons.
Great. So if we take a look at a carbon-carbon bond, what is the partial charge there? 0, right? Those two carbon atoms have a difference in electronegativity, a difference of En, that is 0. And so they have no partial charge character. This bond is called nonpolar, although a better way to think of it is that it's actually a pure bond. And throughout the semester, I'm going to try and convince you that there are some carbon-carbon bonds that have different partial charge character. And I'll use resonance to explain it. But for now, nonpolar, no charges. What about this bond? The CH bond. First of all, do you remember from general chemistry whether this would be classified as polar or nonpolar? Okay, I'm getting both. Do you remember how we can use difference in electronegativity to create these arbitrary lines in the sand and call something polar or nonpolar? The rule was if the difference in electronegativity was equal to or less than 0.4, it's considered nonpolar. And these have a difference in electronegativity of 0.4. I'm not asking you to memorize electronegativities, but I am going to ask you to know the common partial charges, the common bonds. CH is considered nonpolar. Says who? Ada? Who said? Don't say me.
Periodic table.
I know. Good try. I would say the international scientific community.
Sure.
Right. IUPAC, maybe. People have decided that this is nonpolar. The periodic table actually doesn't care. Is there a difference in electronegativity? Yes. So is there partial charge character? Yes. There is an uneven attraction on these electrons by the two atoms. So here's the deal. We're going to call this a nonpolar bond. And I want you to understand where the partial charges go. Are you okay with that? Are you okay with showing a dipole on something that has no dipole? You guys are just giving me blanks here. Can you find comfort in that uncomfortability? Which of these atoms is partial negative in this non-polar bond? Carbon. Carbon pulls on the electrons more than hydrogen. I like to say carbon owns those electrons. All right? Now, in organic chemistry, this bond and the boron-hydrogen bond, which has an electronegativity of 0.1, these are the only two bonds that are considered, these are the only two bonds that we generally don't always put partial charges on. And they're considered nonpolar. There are a few weird exceptions that are considered nonpolar, but everybody always talks about their partial charge. The BH bond is a strange one, and we're going to take advantage of its strange character this semester. Which atom do you suppose is more electronegative? Boron, element 5, or hydrogen, element 1? Yeah, everybody thinks that. But hydrogen actually has a stronger pull on electrons than boron does, by 0.1 difference in electronegativity. So it's barely more electronegative. But who owns the electrons from the BH bond? Maisie? I would disagree. Partial charges disagree. Why does hydrogen have a partial negative? Because it's pulling on the electrons more. Hydrogen owns the electrons. Think about that in the CH bond. Who owns that bond? Carbon. That's why carbon has a partial negative. It owns the electrons. If those electrons are going to stop being a bond, who gets to use them? The partial negative atom. Carbon in CH, or hydrogen in BH. That's the mind frame I want you guys to have. Why does it have that partial charge? Because it owns those electrons. All right, here's another one that is odd. The carbon-iodine bond has an electronegativity difference of 0. That's weird. They have the same electronegativity. And yet no one would say that there is no partial charge character. What does your intuition say about the partial charge character on this bond? Who is partial negative? Iodine. And why is that? Well, iodine is a, well, let's see. First row, fluorine, chlorine, bromine, iodine. Iodine is a 5th row element. So it has electrons in 5s and 5p. Those are big orbitals. And it's just the 2 electrons moving between the orbitals of carbon and the orbitals of iodine. So where are those electrons going to be found more? Around iodine. There's just a better probability of it. Does that make sense? So when the bond breaks, who owns the electrons? Iodine. Despite neither of the atoms technically pulling on it. That idea of size creating that charge difference is referred to as polarizability. Its ability to distribute charge more and take on a charge better because of that. All right, these are the only ones that in organic chemistry I think you'd be allowed to say are nonpolar. The rest of them are going to be polar, and I would like you guys to work together to assign partial charges. C to N single bond, C to N double bond, C to N triple bond, N to H. C to O single bond, C to O double bond, O to H. CF, CCl, CVR. Work together in your groups, assign partial charges, and when you're done, first come, first serve. Put partial charges on 2 of the bonds up here. Okay? Go. Such a team player.
Are these the markers?
Yes, sorry.
No, it's like I don't want to accidentally.
You guys want to put some up? So what are you thinking? That when carbon shares more than one bond with nitrogen, the difference in electronegativity changes?
Oh, I see what you're saying.
Who pulls on the electrons more when it's single versus double? Did you guys put some up yet? Have you? Okay, good start. Find out which two you want to label. Yeah, I mean, how do you guys feel? Feel like you're guessing? So electronegativity is a value given to an element. Well, let me ask you this. If carbon and nitrogen share one set of electrons versus two, does that change how strong
I think it's gonna be
it
it.
still has the same rule. Yeah. Good question. But same rule. Yeah. Well, there's more to break. And so in that way, they're harder. But actually, MO theory says each additional bond breaks MO theory says the difference between a long limit is smaller.
Boron, I think boron is 2.0.
But it breaks down is very awesome.
I remember
Breaks
So yeah, it's technically both a halogen and a first alkynes, whatever this first easy for.
But that doesn't really have anything to do.
Yeah, it's like it can be treated as a halogen. It both has one halogen and also missing one, so it's just really weird.
Good to have you. How do you feel on this?
No, actually, so hydrogen is
Which one is it?
has a I know these numbers. Hydrogen is 2.1, oxygen is 3.0.
You want to put one of them up there? There's only 4 left.
Oxygen, I think, is the second most.
Knew you put 2 up?
I think chlorine
Just one. Okay. It's okay.
I'm just trying to remember the numbers I looked up.
I have 2 left. Has anybody from my middle table put any up yet?
Negative.
How about Jason puts up 1 too? Jason and Aiden?
Sure.
Put up 1. Thank you guys. What did you notice about partial charges on carbon? Usually positive. How often does carbon own the electrons in its bond? Almost never. So when carbon goes through chemical reactions, it almost always loses its electrons. which means it will need to accept electrons from something else in order to get back to an octet. What about hydrogen? What charge does hydrogen usually have? Positive, except for in that case with boron. So what happens when hydrogen goes through a reaction and a bond that hydrogen has to something else breaks? Where would those electrons, those bonding electrons, go? Can hydrogen keep them and walk away from the bond? No. What atom keeps them? The other atom keeps them. Exactly. This is the idea of polarity. It helps us understand how bonds are going to break. We're going to be breaking a lot of bonds this semester. A lot. And I want to communicate about them in terms of who owns the electrons and who keeps the electrons. Partial negative owns them, uses them, keeps them. Partial positive loses them, but can also accept new electrons. It's a magnet. That end of the magnet, that partial positive, is pulling on new electrons. Because the other end of the magnet, the partial negative, is already pulling on some electrons. It doesn't need electrons from something else. You guys okay with that analogy? Partial positive is a magnet that accepts new electrons, gives up the ones it already has. Okay. Now here's a good way to apply this. You guys picked a molecule. There's a lot of bonds in there. Go through and label those bonds with partial positive, partial negative. Think about the polarity. Some people don't like representing these bonds. Does anybody have my blue marker? Some people don't, oh, it's here. They don't like representing these bonds with partial negative, partial positive. That Greek letter feels maybe ambiguous to them. Some people like having the dipole arrow. The electron points towards where the electrons are being pulled. I said that weird. The arrow points to where electrons are being pulled. And this little cross at the end, that's the positive side where the electrons are being lost. So, in all of these instances, you could replace partial charge character with a dipole arrow. Okay? Jason?
Wait, so on the carbon-bromine one, why is the bromine less electronegative than the carbon?
Oh, I guess I didn't proof all of them. Yeah, and I didn't see who did it, so I don't want to, no shade.
I definitely thought I was looking at the carbon chloride, and then I got flustered because I wanted carbon chlorine, and somebody wrote it in green, and I was like, oh wait, it's taken. And
That's fair.
I get there and then embarrassed.
So actually,
Sorry.
the CF I think got two. The CF got green and red. And the halogen was more electronegative, partial negative. And then down here, it is true. Carbon, partial positive. Bromine, partial negative. I haven't looked at the electronegativity values. I want to say it's possible that CBr borderlines not being polar. But again, these are the partial charges. This is how the bonds will break. Thanks for catching that, Jason. And I think we have one that didn't get an answer, huh? The CO double bond. This was the main question that I heard from all of you. Was how does the double bond change the partial charge character? And I think after talking with you, we decided the electronegativity of the two atoms doesn't change. And just because there are more electrons involved, doesn't change who pulls on them stronger. We could go through this exercise, right, of bond line structures, and we could draw partial charges. Can somebody tell me in my bromobenzene where there would be a partial negative charge and where there might be a strong partial positive? Jackie? Uh-huh. And a, good. And there's technically a very small partial negative, partial positive on all the CH bonds, but this would be the most significant. What about here? Elise, any partial charge character to note? Good. And surrounding it on both sides, the hydrogen and the carbon have a partial positive. Great. Yvonne, any partial charge character to note here? Yep. Carbon, partial positive. Good. And so on and so forth. Okay, good exercise? Good review? Great. I'll leave these molecules up so that you guys can get those down for a little bit. Now we're going to talk about acids and bases. This is the process of electrons. Oh, I didn't want to talk about acids and bases yet. I'm sorry. Actually, there's something on my notes, something you need to be able to do that I didn't put on the learning objectives list. So I'm going to update that learning objectives list. I wanted to segue from this into intermolecular forces. Also called IMFs. There's three main IMFs we're going to deal with this semester. Three main IMFs that distinguish organic compounds from each other. The weakest has three names. One of them is called dispersion forces. Remember I told you that everything is a magnet. If you can move the electrons on anything to a certain region of that thing, one end becomes partial positive, the other end becomes partial negative. And then the electrons keep moving, and that partial positive, partial negative fluctuates. That's an incredibly weak magnet because the partial positive, partial negative is never constant. Dispersion forces, also called London dispersion forces, not for the city, but for a person. Also called induced or temporary dipoles. No, it was something else. Induced dipole, also called van der Waals forces. Two dudes that tried to claim this with their name. Instantaneous dipoles is what they're sometimes called, which I don't like because it makes it sound like they are there, but they're only there for an instant. They're induced by the movement of electrons. These are incredibly weak forces, but everything has them. Everything feels this. So I want us to consider a few samples of molecules. First, a hydrocarbon chain. 6 carbons. And I'm going to draw 3 of them. All of the bonds in this molecule are nonpolar. Despite that, the outside of them is all the same. It's all partial positive. There's no region of this molecule that's more negative or more positive. So this is basically just nothing, a very bad magnet. So it experiences dispersion forces between its molecules. All right, the next force Dipole, dipole. Requires a permanent dipole. Some large difference in electronegativity, some strong partial negative, partial positive character. Electronegativity difference greater than 0.4 and polar. Keep in mind, some molecules have polar bonds but are non-polar molecules, like CCl4. Polar bonds between all the carbons and chlorines, but all the chlorines on the outside are the same. So the molecule doesn't have a region that is highly positive and a region that is highly negative. So let's consider our next molecule. Instead of having these 6 carbons, I'm going to replace the last carbon group with a chlorine. And we've got partial charge character. Partial negative on each chlorine, partial positive on those carbons bonded. Now you'll notice that this molecule also has some van der Waals forces. There's van der Waals forces between these hydrocarbon chains. Those are long and they interact with each other. But there's even stronger forces here between the partial positives and the partial negatives of neighboring molecules. This is familiar so far? What's our next one? Sarah? Hydrogen bonding. One of the worst named interactions in chemistry. Despite being called a bond, it is 10 times weaker than a bond. Oh, maybe I should check my notes. Might be 70 times weaker. Regardless, it's not on the same level as a bond, not a covalent bond anyways. So in these cases, you need very specific atoms bonded in very specific ways. You need a hydrogen atom that is bonded either to a fluorine, an oxygen, or a nitrogen. And it needs to hydrogen bond with the lone pair on a fluorine, the lone pair on an oxygen, or the lone pair on a nitrogen. So there are only specific groups of atoms that can hydrogen bond. Hydrogens bonded to carbon can participate in hydrogen bonding when? Never. So most organic molecules, hydrocarbons, do not experience any sort of hydrogen bonding because all of the CH bonds, they don't have a strong enough dipole moment. Hydrogen bonding is actually just a specific strong type of dipole-dipole interaction. It's these very strong dipoles with very strong dipoles. Okay, so for our molecule, now I'm going to switch to 5 carbons and an OH group. And here, I'm only going to look at the partial positive on H and partial negative on O. And what we're going to show is very strong interaction between the partial negative on O and the partial positive on an adjacent H. Where does hydrogen bonding come in as important? Where have you heard of hydrogen bonding? Will?
Isn't it the reason why water is liquid at room temperature?
I mean, I guess. Yeah, that makes sense. And pressure, standard pressure. Okay, so to compare, another molecule of hydrogen's molecular mass, ammonia, NH3, is a gas at room temperature. And that's because hydrogen can hydrogen bond twice as much as ammonia can, and therefore it has twice as strong of reactions, basically. So it takes more energy to separate molecules. Anybody else? Implications of hydrogen bonding. Water? Elliot?
An amino group is like an NH2, that do stuff.
So amino acids can hydrogen bond. Amino acids have structures that contain, we saw this in our last class, structures that contain NH2 groups, which means there is an NH bond and a nitrogen with a lone pair for hydrogen bonding. There's also an OH bond and oxygens with lone pairs. And then there's OH to the nitrogen's lone pair, NH to the oxygen's lone pair. Absolutely. Amino acids can definitely hydrogen bond to each other. What else? This is a big one. Hayden?
Water surface tension.
Yeah, that's a huge implication. Because water hydrogen bonds so strongly with itself, it has very high surface tension. Elise? Nucleotides. You read my screen. Nucleotides experience hydrogen bonding. And Elise, where are nucleotides found? DNA. So your double helix DNA is a double helix because nucleotides on one side, hydrogen bond with the nucleotides on the other. So notice the lone pair on a nitrogen, the NH bond to the lone pair on an oxygen, the NH bond to the lone pair on a nitrogen. I don't think any nucleotides have OH bonds. Correct me if I'm wrong. They're only NH bonds. Yeah. But we get all these combinations of hydrogen bonding. And it's strong. It's just not as strong as a covalent bond. So the NH bond is stronger than the NH hydrogen bond to a lone pair. So you can separate your double helix of DNA by overcoming that hydrogen bonding. But also, UV light can overcome that hydrogen bonding, cause mutations by splitting apart your double helix. Yeah? Okay. Let's take a look back at these molecules. These structures that we left up, we put partial charges on them. Which of these molecules experiences van der Waals forces? Someone raise your hand and tell me. Good job, Andy. They all experience van der Waals forces. That is just the slight moving of electrons. Okay. Which of these experience dipole-dipole forces? Here? Just these ones on the four. These four on the left of me. This one on the middle and the bottom, they experience dipole-dipole? Yeah, they do. Is that it? Why does the top one not experience a dipole-dipole force? Wood. Is that what you were going to say? There's a strong dipole between C and Br, so they experience dipole-dipole. What about the CO double bond? Strong dipole. It can also experience dipole-dipole forces. So they all experience van der Waals. They all experience dipole-dipole. What about hydrogen bonding? Which of these can experience hydrogen bonding? Only the groups that have the OH, because there are no examples that have an NH. So you're telling me that this molecule can't do hydrogen bonding? It's got lone pairs of an oxygen.
Isn't oxygen's molecular orbital full though because of the double bond?
Yeah, but they would be in those examples too. This molecule cannot hydrogen bond because, Kiara? There's a ton of hydrogens. There's no hydrogen that's bonded to a fluorine, an oxygen, or nitrogen. The only hydrogens here are connected to carbon. Those hydrogens are not qualified to hydrogen bond. They don't have a strong enough partial positive on them to create that strong magnetic attraction that hydrogen bonding is. Okay? Will.
Well, so I'm just curious. So in that case, like, is the reason why the oxygen is not bonding with hydrogen is it because of the double bond? That's what I'm trying to.
No,
That's what I was trying to understand.
the only reason that this oxygen doesn't hydrogen bond with the hydrogens on a neighboring molecule is because none of these hydrogens on the neighboring molecule are bonded to one of these three atoms.
Oh, so like it wouldn't hydrogen bond with another molecule of the same type.
Correct.
Oh, I see what you're saying.
It could hydrogen bond with another
That's
molecule,
what I was curious about.
but not with another molecule of itself.
Got it.
And this is a tricky question. It's one that I'm trying to get the wording down for so that I can actually make it make sense well. And so this is how I want to phrase it. We've got samples A, B, and C. This is hexane. This is 1-chloropentane. And this is 1-pentanol. Those samples. Here's what I want you to answer. What IMF or what IMFs are common between samples of A and B? Samples of them, not mixing them. What IMFs are common? Do they both experience van der Waals forces? Do they both experience dipole-dipole forces? Then the only IMFs common, induced dipole, van der Waals. What is the strongest IMF? Common between samples of B and C. I'm not mixing them. I have a sample of A, I have a sample of B. Those molecules are interacting with each other. What is the strongest IMF common between B and C? Andy? Dipole-dipole. Samples of B, an example of something that has van der Waals and dipole-dipole. Sample of C, an example of something that has dipole-dipole, van der Waals, and hydrogen bonding. So the strongest IMF, they both share van der Waals and dipole-dipole. The strongest IMF is dipole-dipole. These questions seem to trip students up based on thinking that it's this molecule interacting with that molecule, but I want you to often think about them as samples of those molecules. Two separate containers that are pure samples. what are the IMFs going on in those two samples that are common between the two? Yeah? Okay. I want to give you guys a break so that you guys can get up and get your blood flowing a little bit. So why don't we take about 5 minutes and come back in here to transition into our next topic.
Like two of these next to each other, you wouldn't end up with like this end oriented off the oxygen with like hydrogen interactions.
Nope, because there's no hydrogen that has a strong enough positive charge. It only gets a strong enough positive charge to hydrogen bond
Okay.
if it's bonded to one of these atoms.
Yeah.
So you'd get a dipole-dipole interaction from the CO double bond groups,
Yeah.
but you'd never have hydrogen.
Okay. Right. 'Cause
Going up to a
carbon
hydrogen.
isn't electronegative enough to get it strong enough.
Exactly.
Okay.
The carbon's not strong enough
Yeah.
to set up the hydrogen.
Okay. That makes sense.
Good. Me too. If you guys have your molecules, start looking at them. Think about those partial charges. Think about what IMFs they can interact with. All right, guys. So, our next topic is resonance. Who knows what resonance means? Who learned resonance in Gen Chem? Yeah. Huh. Who did not learn resonance in Gen Chem? And you're confident on it. Okay, I'm going to assume the rest of you mean you're not sure if you remember or not.
If I did, I don't remember.
So I think of resonance as two things, depending on whether you're looking at valence bond theory or MO theory. Resonance is the movement or the delocalization of pi electrons. So there's a great example of resonance in the anion carbonate. Carbonate has 3 resonance forms. One, where the top oxygen has a double bond. One, where the bottom left oxygen has a double bond. And one, where the top right oxygen has a double bond. Now, students usually come to me and say, those are the same molecule, you just rotated it. Well, I get it, that's fair, but there are 3 different atoms, and imagine that we lock those atoms in place. All 3 of those are valid. So where is the negative charge? It's delocalized. It actually looks like the pi bond is moving around, so it looks like movement of pi electrons. But remember, MO theory says you're probably drawing a structure wrong. MO theory has an answer for what this is. And MO theory's answer, if we're looking at energy, is that there are 3 pi orbitals. One of them is completely in phase with 3 p orbitals. One of them only has 2 orbitals drawn, and then the top one has 3 orbitals completely out of phase. Where the orbitals change sign or change phase is a node. With increasing energy, there are increasing nodes. That was true for all MO diagrams. But look at this orbital in the middle. This molecular orbital, which spans 3 nuclei, only has electron regions around 2 of the nuclei. That third nuclei that's here and here doesn't experience the electron orbital. The electron is never found in that spot. So you take any 3-atom system, let's say for right now, 1, 2, 3. 1, 2, 3. And you put those nuclei here. 1, 2, 3. And then you start to fill in pi electrons. Well, we know there's a pi bond, so that's 2 electrons. And we know that there's a lone pair here that can actually seem to become delocalized to up here. So that's involved in the pi system. So there's a second 2 pi bonds, 2 pi electrons. And where do you find that second set of electrons, that second pair? Only at atoms 1 and 3. Only here or here. MO theory says the orbitals delocalize the negative charge. Valence bond structure, bond line structures say the electrons are moving. So we relate these by a double-headed arrow. Those of you that learned about resonance before, what is this arrow called? A resonance arrow. Good. Just your double-headed arrow. It's different than two arrows going in opposite directions, which is equilibrium. This is double-headed. Which of these resonance forms is the true form of the structure? None of them. In fact, we could draw a resonance hybrid that says these three forms are approximately equal to a double bond between each of them and an overall 2- charge. But even that is flawed, because now I don't know how many lone pairs to draw in, and I have a hard time really understanding things. But that -2 charge is not on just these two atoms. It's really delocalized across all three of them. Each atom has a -2/3 charge. That's resonance. Now, this is not necessarily an organic molecule. So let's look at examples of resonance in an organic molecule. Well, if all it is the movement of pi electrons, then I can take something like this. And oftentimes we'll put resonance forms in these brackets. I can take this CO double bond and I can break the electrons according to the dipole and say the pi electrons have moved. So that's a resonance form. But these two forms are not created equal. Rule number 1 about resonance contribution. That's another way of saying stability. How stable is a resonance form? Rule number 1 is minimize charge. These are two resonance forms of the same structure, but they do not have the same charge. The structure on the left is more stable. It contributes more to what the molecule actually looks like because it has minimum charges. Here's another example of a compound. And this compound exists in nature. This is a natural organic compound. That's a 6-membered ring with oxygen at the top of it and a positive charge on the carbon to the left. A couple of double bonds in there. Its resonance form on the right, 3 alternating double bonds. Is charge minimized between the two resonance forms? Is there one that has more minimum charges? So these are equal according to minimizing charge. The one on the right is a major contributor. What's the difference between the structure on the right and the structure on the left? The only difference, I know you're looking at which atom the charge is placed on. There's a bigger difference, and that is octets. The carbon on the left with a positive charge doesn't have an octet. The structure on the right, every atom has an octet. The structure on the right is major. This is more stable, and that's because of rule number 2, maximize octets. And really, this idea of maximize octets, it applies to carbon, just carbon. Nitrogen with a positive or a negative charge has an octet. Oxygen with a positive or a negative charge has an octet. It's really only carbon with a positive charge that loses its octet. So you could also say avoid carbon with a positive charge. If you avoid that, you maximize the octet. Now, consider this smaller molecule. Is there any difference in octet? No. Every atom has an octet. Well, sorry. First rule, the most important rule. Is there one form with minimum charges? No. They both have a negative charge. Then consider octets. Is there one form that has maximum octets? No. They both have octets. Nitrogen with a negative charge, 2 lone pairs. Oxygen with a negative charge, 3 lone pairs. Both have maximum octets. How would you rank these? Which do you think is more stable? Nitrogen holding a negative charge or oxygen? Dylan? Nitrogen is more electronegative? Anybody disagree? Carbon, nitrogen, oxygen. Oxygen is more electronegative. That's why oxygen has more lone pairs for itself in general. Because oxygen, that's not totally true, but I do, and it's okay to think of it that way sometimes. Oxygen is more electronegative. So holding a negative charge, oxygen is better at that. This holds the negative charge. And our rule here, our third rule is appropriate charge placement. Other than carbon, don't place the positive charge on carbon because that would minimize your octets. So predominantly here, we're looking at negative to oxygen, positive to nitrogen. Now, I want to point out a couple of things. 80% of the time, resonance structures involve 3 atoms. It's the movement of a charge from atoms 1 to 3, and the displacement of a pi bond from 1 to 2 to 2 to 3. 20% of the time, resonance forms involve just 2 atoms sharing lone pairs. But here we have again 1, 2, 3 atoms where the charge moves from 1 to 3 and the pi bond relocates. Okay. Part of what we want to learn in this class is how do we show the movement of those electrons. And this is our learning objective here. Electron arrows. These show bonds being formed and bonds breaking. Bonds can form from bonding electrons being used to do something else or lone pair electrons being used to do something else. But here's the best rationale that I can give you. When bonds break, they break to the partial negative atom. that atom keeps the electrons. And when bonds form, they form from the partial negative atom. We're going to be considering two things with electron arrows: bonds breaking and bonds forming. They break towards the atom that owns them, and they form because an atom that owns them, it decides to do something else with them. From partial negative to partial positive. So it's important to be able to identify partial charges in your bonds so that you can understand how those bonds will break. Let's start up here with carbonate. Could you show the transformation from the first to the second resonance form using electron arrows? Notice what changes. A single bond becomes a double bond. A bond forms. A double bond becomes a single bond. A bond breaks. When a bond breaks, it breaks to the partial negative atom. So I show my electrons starting at the bond, and I move them to the partial negative atom. That's an electron arrow. When bonds form, they form from the partial negative atom. So here, partial negative atom shares its lone pair, that negative charge, and creates a double bond. I almost hate to say this, but one of the main ways that students mix up electron arrows is that they say, well, the oxygen on the bottom just lobbed up its lone pair to the oxygen on the top. And then the CO double bond took its pi electrons with carbon down to the oxygen on the bottom. Does carbon own those electrons to take the pi bond away from oxygen and share it with another oxygen? No. So we said CO double bond breaks, correct? Who owns the electrons? Oxygen. Who gets to take the electrons? Oxygen. Can you do the same thing to show the transformation from the second to the third resonance form? Show the bond that breaks, show the bond that forms. Have you identified the bond that breaks? Then show the electrons breaking to the partial negative. Have you identified the bond that forms? Then show electrons from the more negative atom donating electrons to form that bond. Want me to look at it?
Oh, yeah, no, it's not you.
So here I wouldn't start at the carbon. I'd start a little bit more in the middle. Are you going to form this one? So you want to show on this, the arrows and this to form the dot. You showed this, which is great. Good start. Jason, you got it. Bruce, you got it. You got it. You just don't have the negative charge anywhere. And what can you never assume?
Negative charge.
Charges. Good. Jackie? Got it. You guys got it. Makes sense, huh? Good. Glad to hear it. I didn't see everybody's. Sorry. Let's draw them in. This bond breaks. Who owns the electrons? Oxygen. this bond forms. Where would those electrons come from? Oxygen.
Starting to see why we need this molecule to breathe.
Not that molecule.
No, sorry, atom.
Oh, yeah. What about this? Can we show electron arrows on the left structure to make the right structure? How many arrows needed? 1. There's only one change. A bond breaks. Which way does it break? Towards oxygen. Notice that I'm starting in the middle of the bond. By the way, which line is the pi bond? Exactly. That's why bond line structure is not as good as MO theory. Either one. I talked over somebody, but either one is the right answer. Can we show anything here? What's the change? Does a bond break? No. A bond forms. Now, I cannot show electron arrows without showing electrons. Here, the negative charge implies my lone pair of electrons. Here, my bond are my electrons. I don't have any electrons on oxygen yet, so I have to draw them in. I said that we can generally assume lone pairs unless we need them for arrows. From oxygen to carbon. Does anybody feel brave enough to add arrows to this resonance form? Got a marker. Oh, it's got your name on it too. That was funny. Mal, come on up. Yes, sorry. Do your best. Great job, Mel. We're not going to draw anything on the right because we're only showing the formation of the thing on the right. The only thing I would change, Mel, is rather than starting at what looks like the carbon atom, is I would have this arrow start closer to the middle of the bond. And then I'd have it end closer to the oxygen atom. Perfect. Thank you. Come on, guys, give it up for Mel. That was brave. None of you did it. All right. This is resonance. Resonance is not different molecules. Resonance is the same molecule shown in different ways, but sometimes those different forms contribute different to the molecule. Some are more stable than others. But either way, all resonance forms explain a little something about the molecule. Okay? Resonance gets introduced now because we need to use it as a justifier in acid-base chemistry. We're going to be considering two types: Bronsted-Lowry, acid-base pairs, and Lewis, acid-base pairs. Typically, I start with Bronsted-Lowry, but today I'm actually going to start with Lewis because I think I've decided that Lewis acid-base pairs are actually easier to connect to resonance and arrows. A Lewis acid is described as an electron pair acceptor. An electron pair acceptor is a molecule which likes electrons. You may even say loves electrons. And so we call these electrophiles. A Lewis base is a compound which donates electron pairs. So you might call it tricked you. Something that likes a nucleus to donate its lone pair to. A nucleophile. I don't mind electrophobe, but the Lewis bases usually just share their electrons. So they never really get rid of them. But I kind of set you up for that. Sorry. So there's a few really common examples for things like this. Take tetrahydrofuran with the molecule borane, BH3. Borane is an electron deficient compound. Boron doesn't have an octet, and that makes it neutral. Boron has 3 electron regions with an empty p orbital. Diethyl ether, a common solvent, can donate a lone pair to that empty orbital on boron. And this makes what's called an adduct. A new bond has formed. Notice how that bond formed because the electrons went from partial positive to partial negative to partial positive. 2 charges are formed in this compound. Can you tell me the charge on oxygen? Look at that bonding pattern. 3 bonds. What's your gut say? Yeah, it just gave up some of its electrons. Oxygen becomes positive. Boron is one of the weird ones. Boron has 3 valence electrons. When it has a full octet, it's negative. Can you tell me which of these 2 compounds, borane or diethyl ether, is the Lewis base? Good. Diethyl ether is our Lewis base. The electron pair donor. Borane is our Lewis acid. Then there are some weird examples. Take, for instance, H2C double bond CH2 with HBr. Notice I'm drawing the HBr bond. Electron arrows start from the CC double bond, and they move to the hydrogen, and then the HBr bond breaks. And this gives me CH3, CH2 plus, and Br minus. Which compound is the nucleophile, the electron pair donor? CH2, CH2. Good. It's donating not from a lone pair, but from a pi bond. Our nucleophile, our Lewis base. Now, if you're like me, I look at that HBr and say, there's too many electron arrows going on. Bromine is taking electrons too. Isn't it kind of donating electrons to itself? Doesn't that make it an electron pair donor to itself? Not really. It is accepting electrons, and bromine has to leave because of that. This is the electrophile. All right, the last one, the one I want you to try and apply something on. This is CH3O minus and H3C with a long bond to Cl. I'm not going to show you the arrows, and I'm not going to tell you which is which. I'm just going to tell you that the product is CH3OCH3 and Cl minus. Can you draw in the electron arrows to show the formation of this product? And can you label the Lewis acid and the Lewis base? Does it have any electrons? Good. Yeah. So you said a bond forms between O and C. Bonds form from the more negative. Good. Good story, Mom. You're recognizing the carbon-chlorine bond breaks, right? When a bond breaks, it breaks two the more negative. So show the bond breaking two the more negative. Yeah? And then when a bond forms, great. There's no H. Oh, if there was, it wouldn't be a charge. It would work, it would do it, it just wouldn't have a charge.
Okay, yeah.
Oh, you went to the product. Oh, gotta draw it to there. And then again, you drew it to the product. Okay. Yeah. Beautiful. Great. Only thing I'd maybe do better is starting at the charge. But okay. It's close. I'd say it's yes. Nailed it. Anybody want to put theirs up? Well, you're not showing the bond forming to the carbon.
I erased that because I didn't think
All
that
the
you
way
did
over.
that.
All the way over to the carbon. Because there is a new OC bond. Yes. There you go. Here, I'll give you the black so it matches. Jackie's going to put her arrows up. Does somebody else feel like labeling this as Lewis acid and Lewis base? Nucleophile and electrophile. Got a red marker. Great job, Jackie. Great. Thank you, Aiden. I gotta say, guys, this is the best students have ever done with electron arrows on the first day. Great job. I mean that. Round of applause to yourselves. You guys need some self-confidence. Do I tease too much?
Nah, it's just 6:30.
It's not 6:30, it's 6:37, and I have to talk about Bronsted-Lowry acid bases. All right. Questions about Lewis acid bases? That's pretty much all there is to it. Lewis decided on picking the broadest definition of acid base. All other types of acid bases are Lewis acid bases, but not all Lewis acid bases are the other types. That's the all circles are all squares are rectangles, but not all rectangles are squared idea. All other acid bases are Lewis acid bases, but not all Lewis acid bases are Bronsted-Lowry. Bronsted-Lowry instead decided these definitions. Bronsted-Lowry acid is a hydrogen ion donor, and Bronsted-Lowry base is a hydrogen ion acceptor. Sorry, my acceptor looks really cruddy. So we can write a generic equation here that says HA becomes H plus and A minus, and B plus H plus becomes BH plus. And maybe you guys saw equations kind of like this in General Chemistry 2, maybe even in Gen Chem 1. We can sum these two equations. Notice that H plus is on both sides. And we can say that HA plus B is equal to BH plus and A minus. Do you know the name of H plus? Sorry, proton, actually. H plus is proton. Do you know the name of BH plus relative to B? Conjugate acid. The base becomes a conjugate acid. And the name of A minus relative to HA? Conjugate base. Wait, so I just took an acid and a base and I made an acid and a base? Well, aren't acids H plus donors and bases H plus acceptors, so can't the reaction go the other way? Can't this acid-base pair that just formed now react to form this? Equilibrium arrow. Two arrows pointing in different directions. I have a bad analogy for this. It's like if you take the makings of a sandwich and you start making a sandwich, and then somebody else comes and starts taking the sandwiches you just made and disassembling them. That's the equilibrium. At some point, you're going to be making sandwiches at the same rate that they are taking your sandwiches apart, and you'll have dynamic equilibrium. You're at kind of the same number of sandwiches, but you keep making sandwiches and they keep taking them apart. And you just fight back and forth. It's weird, right? Because who's taking apart sandwiches? But it gets the idea across. As soon as you start making these compounds, the conjugate acid and conjugate base, they start taking themselves apart until you reach a point at which you're at equilibrium. Now we rank the ability of a compound to be an acid by how well it creates H+, and then we report that as a pKa. pKa is opposite the log of H+ concentration times A- concentration over the concentration of HA. That's honestly not an equation you'll have to plug into in my class. So if you don't want to use it, I don't care. Here's the idea. Something that's really good at making H+ is going to have a concentration of H+ that is larger than the concentration of HA. That is a ratio larger than 1. The opposite log of a number larger than 1 is negative. So a more negative pKa is a better acid. A more positive pKa is a bad acid. But honestly, the way that we typically think about very positive pKa's is that it has a great conjugate base. You guys know I posted my videos from the summer on YouTube. Has anybody been to that YouTube channel? A handful of you? I've got it linked on the top of our class recordings page. So if you go to that class recording on the homepage, it's a link to my YouTube playlist. I don't know that I'm going to be able to explain the factors of this in less than 7 minutes. I'm nervous. But I really don't want to push back your unit test, and this is the only thing standing between us and your unit test. So I'm going to encourage you to check out that video for better explanation. But I'm going to give you the list of things that impact whether something is a good acid or a better base. Comes down to these factors: charge, atom, resonance, induction, and orbital. And this is not a hierarchy. These have constructive and destructive effects on pKa. So when I ask you questions about these, it's generally saying either a compounding effect that makes something a better acid, or it's all in the same range. In terms of charge, things that are more positive are generally better acids. H3O plus is a better acid than H2O, is a better acid than hydroxide. And then we can make that same application to organic compounds. There are tons of exceptions, such as H3O plus is a much, much weaker acid than HSO4 minus. Atom breaks down into two parts. In a row, more electronegative atom is a better acid. But in a family, a larger atom is a better acid. You can prove this by taking the link on our homepage that has functional groups and pKa's and looking at the pKa values of HF, HCl, HBr, HI. HF is the most electronegative. It's the worst acid in the family. HI, least electronegative, the best acid. And that's because when HI becomes I minus, it polarizes that charge. It spreads it out and it becomes a very weak minus because it's spread out over a huge amount of space. Resonance. This one's challenging because to decide about something, you need to think about the conjugate that it makes. Increased resonance in the conjugate makes for a better acid or base. If the conjugate that it forms, BH plus, can spread that positive charge around by delocalization, it's going to be very stable, and it makes it a bad acid going backwards. So it builds up, and the equilibrium favors this side. If the conjugate base is delocalizing that negative charge is not good at being a base in the reverse. It builds up, and the equilibrium favors that side. So the more resonance in the conjugate, the stronger the acid or base actually is. To analyze this, analyze the resonance in what it forms. Induction is actually a push and pull of electrons. Anybody use an induction oven? You do?
Oh, I have.
I never have, I don't think. But it uses electric current or magnets, I think, right? It induces heat by magnetic stuff. Well, this is a push and pull. So one of the biggest applications is the more electronegative atoms you have, the better an acid you have. And actually the opposite is true. The more electropositive groups, do you know what electropositive is? It's the opposite of electronegative. Electronegative pulls, electropositive pushes. The more electropositives is a better base. And then the orbital is kind of a strange one, and it really applies most to carbon. What we say is more S character. I spelled that wrong. More S character is a better acid. That means sp is better than sp2 is better than sp3 carbon. sp has 50% S character, sp3 has quarter S character. And again, this has something to do with the conjugate. That lone pair on the conjugate base is less repelled when it's in an sp orbital. It's highly repelled in an sp3 orbital. The base is less stable. I hate leaving you guys like that. I'm so sorry. But trust me when I say these notes will help you get through that unit test. Granted, you may have some questions at the end of it. But I feel very confident that you're going to be able to take those 2 attempts on part A and master the concepts in between, and that you'll take your part B and feel good about applying bond line structure, arrow pushing, things like that. Okay? Have a great weekend, guys. I'll see you on Monday when we move into Unit 2.